Welcome to the Explainer. Today, we're embarking on a really fascinating journey into the chemist's toolkit. We're going to uncover exactly how we isolate pure substances from all those messy, everyday mixtures around us. Okay, so let's dive right in with the most foundational question we can ask. Why do we even go through all the trouble of separating complex materials in the first place? I mean, it's not just for the sake of having a tidy laboratory, right? It's literally the foundation of how we understand the material world. And that brings us to our roadmap for today. We'll be covering the pursuit of purity, separating solids from liquids, mastering liquid mixtures, paper chromatography, and finally, proving purity. All right, Section 1, the pursuit of purity. Why clean matters. So the absolute crucial point here is that we separate mixtures so we can actually study individual components safely. And, this is absolutely vital when we're creating things like medicine that simply cannot harm the end user. Think about it. If a pharmaceutical company doesn't perfectly purify a life-saving drug, those remaining impurities, they could be highly toxic. So purity, in a lot of cases, is quite literally a matter of life and death. Moving right along to Section 2, separating solids from liquids, the basics of extraction. Now, take a look at filtration. It's a beautifully simple setup. It relies entirely on just size differences to separate an undissolved, insoluble solid, like sand, from a liquid like water. It's honestly one of the oldest and most reliable tricks in the book. In this incredibly straightforward procedure, the filter paper acts as your ultimate physical barrier. The tiny little liquid molecules just slip right through the microscopic pores of the paper, becoming what we call the filtrate. Meanwhile, the chunky solid particles get trapped on top, so you're left with a pure liquid in the beaker below and your solid residue up top. Pretty easy, right? But what if your solid is completely dissolved, like sugar in water? You definitely can't filter that out because those sugar particles are just as small as the water particles. Well, that's where we bring in a crystallization setup. Now, you might be thinking, hey, why not just boil off all the water until only the sugar is left? Well, actually, if we boil all the water off super rapidly, heat-unstable substances like sugar will just decompose. They'll basically caramelize into a giant burnt mess. So, to avoid completely ruining our sample, we follow these really precise steps. First, we gently heat the solution just enough to evaporate some solvent until the solution becomes saturated. And we can actually test this by dipping a cold glass rod right into the liquid. If crystals form on it, boom, we're ready. Then we sort of coax those dissolved particles into slowly forming pure, beautiful crystals just by letting the mixture cool down naturally. Finally, we filter those crystals out, wash them with just a tiny bit of cold distilled water to remove any lingering surface impurities, and gently pat them dry. Now, imagine a real-world scenario where you have a mixture of calcium sulfate and magnesium chloride. How on earth do you separate two solids? Well, take a look at their properties. One dissolves in water and the other doesn't. By dissolving this solid mixture in water, we can easily filter out that insoluble calcium sulfate first. Then, we just use the crystallization method we literally just talked about to extract the soluble magnesium chloride from the remaining liquid. It's essentially a perfect 1-2 punch of separation techniques. All right. On to Section 3, mastering liquid mixtures, the art of distillation. This classic simple distillation setup you're seeing here is perfectly designed for extracting a pure liquid from a soluble solid mixture. A really great example of this is getting pure drinkable water right out of salty seawater. The pure genius of this process really lies in these 4 steps. First, we apply heat, turning the water into a vapor. That vapor rises up past a strategically placed thermometer at the neck of the flask so we can monitor the temp. Then the vapor travels down the condenser. Now notice how the cooling water flows into the condenser from the bottom and then out the top? That is super important. It ensures the entire jacket stays completely full of cold water, perfectly cooling our vapor back into a liquid. It then drips out as pure, clean distillate, leaving all that salt entirely behind in the heating flask. But what if we're dealing with two liquids that perfectly mix together? We call those miscible liquids, like alcohol and water. For that, we're going to need to upgrade to a fractional distillation setup. As you can see, the addition of the fractionating column in the second method gives us that higher degree of separation we absolutely need when liquid boiling points are tight. Simple distillation works great when boiling points are hugely different, but when they're super close, you really need that extra column to step in and do the heavy lifting. When you're running this separation, you basically have to watch the thermometer like a hawk. Ethanol boils at 78 degrees Celsius, while water boils at 100. So right at 78 degrees, the ethanol vapors rise up, while the water vapors get trapped in the cooler fractionating column, condense, and fall right back down into the flask. Once that thermometer starts creeping up past 78, you know the ethanol is done, and it's time to swap your collection beaker fast before the water starts coming through. And honestly, you just kind of have to accept that a little bit of wastage between the liquids is an inevitable part of the chemistry process. Okay, moving to section 4, paper chromatography, revealing hidden components. By following these simple steps, we can unlock the hidden components of a mixture. Now, crucially, we use a graphite pencil to draw our start line. Why? Because pencil graphite doesn't dissolve in water. If you used a pen, the ink from your line would separate and completely ruin your results. So we put a tiny spot of our sample, say a dot of black ink, on the line and place the paper in a solvent, making sure the liquid level is sitting just below our pencil line. As the solvent creeps up the paper, it carries the different dyes in the ink mark at different speeds, literally spreading them out so we can see exactly what colors were hiding inside it all along. It's kind of like magic, but it's science. And finally, section 5, proving purity, the final test. So, we've separated everything, but how do we prove it's actually pure? We rely on hard data. We use precise tools, like a melting point oil bath, to slowly heat a tiny sample and observe the exact temperature at which it changes state. An oil bath is fantastic for this because it heats so slowly and evenly, letting us pinpoint the exact moment of melting. Now, if your sample is messy, trust me, these data points will betray you. Impurities actually stretch the melting process over a broad range of temperatures rather than giving you a single sharp point. Specifically, impurities will drag a substance's melting point down, making it melt way earlier than it should, and conversely, they push its boiling point up, making it boil later than normal. Ultimately, this brings us to our strict definition. A truly pure substance is perfectly consistent. It doesn't melt over some weird range. It gives us one sharp, specific temperature reading. Or, if we're using paper chromatography, it leaves just a single, solitary spot on our testing paper, proving absolutely that it isn't hiding any extra components. So as we wrap up this explainer, I want you to just look around your room right now. Ask yourself, how many of the manufactured items, foods, and medicines you see every single day rely on the very journey of purity we just mapped out? From the purified water you drink to the exact safe compounds in your medicine cabinet, the chemistry of separation literally touches almost every aspect of modern life. Thanks so much for diving into this structured journey with me today, and keep exploring those amazing, complex mixtures all around you.